The last thing I'm going to write, I'm going to give you homework, very simple homework. When you in potential problems, we have nabla square u of x equal to 0. And the fundamental problem, when we have u asterisk of x comma xi equal to the Dirac delta of x and xi. Okay? Now, the fundamental solution you will get here is equal 1 over 2 pi ln r for 2D. I want you to verify that nabla square u asterisk of x and xi will equal to 0 when you substitute this one here. It will get 0 because it is 0 everywhere except at the when xi equal to 0, it will blow up to infinity. You should verify this. I want you to verify this using index notation. I want to verify this using Cartesian coordinate notation. And I want you to verify this using polar coordinate system notation. You have to verify this, and you'll see how easy is the index notation when you do this. By this, something is left with me, how to carry out the integration by parts. So this is, we'll leave it homework. I will give just 1 minute for the integration by parts. This is homework. Just one slide, but it will be very, very useful. For example, if we have integration over the domain of any kernel f comma alpha times, for example, u comma beta. Okay? So when I carry out the integration by parts, I will say, I will take this one as the first function times the derivative of the second function, the integral of the second function, sorry. U, here I integrated with respect to beta, so I have to multiply by n beta, and this is a boundary integral, minus the integral of the previous integral, times the derivative of the first one with respect to the same. This is alpha, sorry, I'm sorry. So f comma alpha beta, comma alpha beta. Okay, again, the first function times the integral of the second function, minus the previous integral times the derivative of the first with respect to the index that I integrate with respect to it. Or the same integral could be equal. I will take this one as the first function, u comma beta, times the integral of this one f times n alpha minus the integral of the previous integral f times the derivative of this one, which is u comma beta alpha. Both expressions are similar. Okay, this is very important because because of that I don't like uv and vdu and all of this. I usually read it. The first function times the integral of the second function minus the integration of the previous integral times the derivative of the first. Just always put this in your mind. We will play with this with boundary ellipses. We will play with these identities with boundary ellipses. Be careful. Here, in order to be able to use integration by parts, I didn't write f alpha and u beta. No, I put f comma alpha and u comma beta. So what I need potentials. I need derivative of a function. I need to represent my function as a potential function. This is very, very important in boundary ellipses. If we are able to represent our intensity function as a potential of other certain function or any other function, we will be able to transfer any domain integral to the boundary and to play with this. That's it. Okay? Any question? I'm ready for any question now.
Yeah, thank you, Professor.
I think today is a bit tasty.
I think from the basic to try to little bit complicated, but I think the dummy index is very important tool.
Yes.
And
yes, because
and
you can generate the direct potential function. For example, we can write, as Professor Fu said, if we have a function, certain function g, for example, we can write it as f comma alpha alpha. This is what Professor Fu is saying. You are searching for a function, a Laplacian of a function. Once you have it, you will be able to do anything in boundaries. Okay?
Yes. Yes, I think if you're using the dummy index, so the 2D, 3D
yes.
all become very simple.
Very simple. One
equation.
expression. Yes, true.
But if you using it, you should be very carefully, because sometimes it's not like the.
Yes, I know.
Yeah.
You will stay days and hours looking for a mistake, and as mistake is very, very simple. For example, when you move from 2D to 3D, the Kronecker delta alpha alpha equal to here 2, and here is equal to 3. This can change all of the life you have.
Yes. So, any question? Or someone?
Has anybody raised hand or something like that?
I think maybe they need the time to
digest or something like this.
Yeah, to understand everything.
Still, I will write again my number. This is my number, plus, I think, plus or 20. This is for Egypt, and 12 7 7 8 6 6 8 3 3. This is, I have it on WeChat.
Yeah.
So you can contact me at any time of the week, and I will reply direct. Okay?
Yes.
Okay.
Okay, so we have the homework. Yeah. So maybe all the students will try it, and
the next time I will start with potential problem in direct and direct formulation. We'll end it up, and we'll cover also, maybe we'll cover the circular disk idea, and dipoles, and even line sources, all of these ideas with the history. I like when we talk, or even when we teach mathematics or mechanics or anything, it's very important to teach the history of mechanics and the history of mathematics, in order to show students how the idea appear in its normal direction, not from the end to the beginning. No, I wanted the history tell us the appearing of the idea itself. Okay?
Yeah, you are right. I think that's important. So yeah, they have that soul, then they can create some new things.
Exactly. Yeah. We are teaching students, because we are looking for innovators. We are not looking for people who solve problems. We are searching for people to innovate. Okay?
Okay. So if no questions, so let's thanks Professor. And also
I really would
thanks
like to
all
thank you, Paul, for this opportunity, and I always stay all of the week looking forward to see you again in the coming week.
Yes, and also thanks all all you joining us, and I think see you all next week, the same time,
Okay.
and also the same number. Yeah. Okay. Bye.
Bye.